Okay, so we've kind of talked about these along the way, but I wanted to formalize it to make sure that we realize that we can apply this to any function we run into. So the first one, f of x plus h. Okay, so what that means is we are adding a number to the variable in our equation. So for example, we just looked at the absolute value. So let's talk about that. This would be something like the absolute value of x plus 3. Or if we were talking about doing this to a quadratic, that would be like x plus 3 squared. Or we've done exponential functions. This would be like e to the x plus 3. Okay, we're adding the number to the variable, to the x in the equation. What it does, does anybody know what that does? As far as moving the function, moving the graph, if we were comparing it to just the plain absolute value of x, does anybody know what the absolute value of x plus 3 would look like? It goes to the left 3 units. Okay, left, and we're going to say h. Okay, keep it general. That's what we've got here in the table. I just used 3 in my specific example, but it moves left h units. So similarly, f of x minus h is going to move to the right h units. So when we add or subtract it from the variable, inside the function, inside the absolute value, inside the square, inside the exponential, it moves it the opposite of what we would expect it to. Okay, but it does affect the x values. So it is a left and right thing. It's just the opposite of what we would expect. Plus, we would think would be right. Okay? Now, slight difference, f of x plus k, the plus k comes after the function. So to compare it, we would be talking about the absolute value of x plus 1, okay? Or x squared plus 1. Or e to the x, and the plus 1 comes after the exponential expression, okay? What does that do? It moves it up, okay? It moves it up k units. Okay, because we're taking the absolute value function and we're adding 1 to every single y value. Or we're taking x squared and we're adding 1 to every single y value. Or we're taking e to the x and we're adding 1 to every single y value. So that's why it moves it up k units. So f of x minus k would move it down k units. So vertical changes are what we expect them to be. They're what we expect them to be. Vertical changes are expected. So plus up, minus down. A times f of x. We're multiplying our function by a constant. So 2 times the absolute value of x. Or 2x squared. Or 2e to the x. Okay, that says when the absolute value of a is greater than 1, so when we've got a number bigger than 1, that's going to be a vertical stretch because you're multiplying all your y values. Okay, you're multiplying all your y values, so you're making the y values bigger, so you're stretching that function up. When a is less than 1, so we're talking like 1/2 times the absolute value of x, you're taking all those y values and you're multiplying them by 1/2, so this is a vertical shrink. And then the last one, negative f of x, a negative in front of the entire function. So, for example, negative absolute value of x, negative x squared, negative e to the x. Okay, that negative in front of all those, that is going to reflect, that's the word they're going to use, reflects across the x-axis. You're changing all the signs of your y values. Okay, negative f of x changes the sign of all the y value, so it reflects it across the x-axis. Most of the time, like with these three functions, originally, they were all positive. The absolute value of x, all the y values are positive. X squared, all the y values are positive. E to the x, all the y values are positive. So when you put that negative in front of it, it makes all those y values negative, so it's below the x-axis instead of above. If you have a function that crosses, okay, the x-axis, part of it's above, part of it's below, those two pieces are just going to kind of flip, okay? Now, I think these are very simple concepts, but they will kind of ask you, I've seen them use the h's and k's and stuff in a problem. They don't necessarily give you a specific value. Or they may say, well, what would the translation f of x plus h do if h was equal to -5? Okay, so you got to realize you got to kind of plug that in and then realize that -5 is going to move it right 5 units. If you forget them, all you have to do is compare it to an original function. So if we're talking about an absolute value function, we just need to compare it to the regular absolute value of x. So if we were trying to check that whole minus moves it left and plus moves it, no, minus moves it right, plus moves it left, just compare it. Graph the original, just the absolute value of x, what we call the parent function, and then the translation that they're asking you about, and then compare the graphs, okay? That second one just took the entire graph and moved it right 6 units, so that -6 moved it right 6 units, okay? All right, so on our blue sheet, when this is applicable, we're going to talk about the translations, but we're also going to kind of recap all of the characteristics that we have dealt with in the past, and we're going to throw the absolute value in there just to make sure we've got it down pat. All right, f of x is equal to -3x plus 5. I know you have a calculator right in front of you, but let's review graphing a linear function by hand. Okay, the y-intercept is 5, so we go to the y-axis at +5, mark our point, our slope is -3, so my natural instinct is I go down 3, right 1 first. I could have just as easily gone up 3, left 1. Either way, and I'm going to go as far as I can, all the way to the edges of my graph here, and then connect the dots. Technically, we can talk about this one in terms of translations. The parent function here is, of course, y equals x. It is a linear function. Okay, so if we compare that to just y equals x, we've done 3 things to it. Okay, we have, it's a vertical stretch because we've multiplied it by 3, and I can't spell stretch and talk at the same time. Stretch. Wait, is there another T in there? I'm like all thrown off now. I think there is a T in there. Okay. No, there's not. What? There is. Okay. It just looks really weird to me, right? Spelling is not always my strongest suit. Thank you. All right, vertical stretch, because we multiplied it by 3. Okay, it's also reflected. Okay, if you think about the original, y equals x, it is increasing from left to right. This one decreases because it has a negative slope, but another way of looking at it is that negative flipped it over. Okay, so instead of increasing from left to right, it's going to be decreasing from left to right now. And then we also shifted it up 5 units. Because of that +5 there on the end. Okay, so you've probably never really seen a linear function talked about in terms of translations there, but the same thing still applies. Okay, we multiplied it by 3, we multiplied it by a negative, and we added 5 to it. So there were 3 translations compared to just the y equals x. All right, domain and range. What are they for a linear function? All real numbers. Okay. All real numbers. If we look at the graph, starts on the left side, goes all the way to the right side. Starts at the bottom, goes all the way to the top. There are no exclusions there. There are no issues. We can take We can multiply, add, subtract anything we want to any number. All right, number of roots. What is roots another word for? Zeros, okay, zeros. We got a couple more as well. Zeros, x-intercepts, and solutions, okay? Roots, x-intercepts, zeros, solutions, those words are all synonymous with each other. It just depends on which context we're talking about, okay? If you're talking about an equation, it's a solution. But the solution to an equation is also the x-intercept. The x-intercept is commonly referred to as a zero because that's where the function equals 0. Roots, that comes more from your polynomials, that word does. But anyways, doesn't matter what we call it. How many do we have for a linear function? 1. It crosses the x-axis once and only once. That's the only possibility for a linear function. All right, in behavior. If you do not have an in behavior question on the final exam, I will be very, 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 very surprised. I think it's helpful. Label the two ends of your x-axis with the positive infinity on the right side, the negative infinity on the left side. So as x approaches positive infinity, we're talking about the right side of our function. What are the y values doing on the right side of our function? Where are they headed? They're going down. They're going to negative infinity. How about on the other side, on the left side? The y values are going up to positive infinity. Okay, now, increasing and decreasing. What is this function doing as we move from left to right? Decreasing. Does that ever change? No, it's always decreasing. So it's going to be decreasing from negative infinity to positive infinity on its entire domain. From the far left to the far right, it is decreasing. So for increasing interval, you can put NA or you can put none, whatever you want to do. There aren't any increasing intervals for this function. Okay, let's look at an absolute value. Okay, now I know you got your calculator, okay, but we're not going to use it right at this moment. Since we just talked about the translations, let's graph this using translations. Okay, let's talk about what has happened to it. Our original function, I always move the vertex. That's the easiest thing to do. Okay, so the original, just absolute value of x, the parent function, I was trying to change colors here. Okay, y equals the absolute value of x is our parent function. Okay, that's what we're comparing it to. Its vertex is at the origin, 0, 0. So what does that minus 1 do? Right 1. Okay, right 1 unit. What does the minus 4 do? Down 4 units. So we were at the origin, but now we are right 1 and down 4. So our vertex is now at the point 1, negative 4 is where our vertex is. That's the only thing that we did to this function. We didn't multiply it. We don't have a negative in there. That's also the basic shape still exists. The right side has a slope of positive 1. The left side has a slope of negative 1. So I can graph my absolute value function from there without a calculator. All right, so domain of the absolute value function. What did we say that was last week? All real numbers. We can take the absolute value of any number. Okay, we can find its distance from 0, so its domain is all real numbers. How about the range? Y is greater than or equal to negative 4. When you're trying to determine if your range is all real numbers or if it's not all real numbers, you got to look at the graph and you got to ask yourself, do I see a minimum or a maximum value? On number 1, there was no minimum or maximum. The ends just continued on for forever. There was no peak or valley. But in number 2, we do see a minimum there. So we know that it is restricted. If it's a minimum, all your y values are greater than that number. And in this case, greater than or equal to, because we can equal negative 4. All right, how many roots does this one have? 2. Do absolute value functions always have 2 roots? No. What are the other possibilities? Good, okay? It can have 1, it can touch the x-axis, or it can have none. It doesn't have to touch the x-axis at all. Think about when we were solving the equations. Most of the time, we got 2 solutions when we were solving the equations, but sometimes we only got 1 solution, or sometimes we didn't get 1 at all because it was impossible for that function to equal 0. So 2, 1, or none for our absolute value functions. All right, in behavior, what are our ends doing here? Both of them are actually doing the same thing. Where are they headed? They're increasing. Both ends are increasing up to positive infinity. Okay, both the right side and the left side are both going up to positive infinity. Okay, so as we move left to right, now, here's where it's very handy having a graph right in front of you. If you struggle with this part, here's what you need to do. You need to take your finger, you need to start on the very far left side of your graph, and you just start tracing the graph. So what are we doing first, increasing or decreasing? Decreasing. Decreasing, okay? Now, here's what trips people up. Okay, we are decreasing, but we're going left to right. So we're starting at negative infinity, and until we get to 1, we are decreasing. Okay, we use the x values to indicate these intervals. Okay, we're describing the y values, but we're using the x values to tell us where. Then we start increasing from 1 all the way for the rest of our domain until we get to positive infinity. Okay, pretty simple, right? Okay, let's look at number 3. Number 3, negative x squared plus 8x minus 11. That is not in a form where we can talk about transformations. But if y'all will recall, we can put this in what we call vertex form by completing the square. Okay, so let's review completing the square. In this case, remember when there was something in front of the x squared, we needed to factor that out. But we don't do anything to the constant. Remember, we left the constant there on the end. The minus 11 goes to the end. Okay, how do we complete the square? Okay, take b divided by 2. So 8 divided by 2 is 4. We square it, so we get 16. Okay, it has a negative in front of those parentheses, so really we have negative 16 right here. So we have to offset that, and we're going to add 16 to the end. Okay, so we had 16 inside of our parentheses. There was a negative in front of it, so really it's negative 16. We got to offset that negative 16 that we just put in our equation by adding 16. All right, so let's simplify this. This always, always, always factors the same way. That's the whole point in doing it. We turn it into a perfect square trinomial. So it's negative x minus 4 squared plus 5. So there are 3 things that have happened to our function. We have gone right 4 units because of the minus 4. We have reflected. I'm going to leave the word across out because I don't have room. Reflect across the x-axis. And we have gone up 5 units. Okay, so let's think about our parent function, y equals x squared. Think about that parabola. Its vertex is at the origin, and it opens upward. So let's shift it. We go right 4 units. 1, 2, 3, 4. We reflect across the x-axis. I can't really do that part with the vertex yet because I'm still on the x-axis. And then I go up 5 units. So 2, 4, 5. So my vertex is at the point 4, 5 is where my vertex is. Now, if you know much about quadratics, your next step, you go down 1 over 1, down 1 over 1 in both directions. Okay, and then you have a bigger step after that. So personally, I would just like plug in the numbers after that point. So like plug in 2. 2 minus 4 is negative 2. Negative 2 squared is 4. But there's a negative in front of it. So negative 4 plus 5 is 1. So 2, 1 is my next point. Use symmetry because it's symmetric. So we've got 6, 1 as well on the other side. If you plug in 1, plug 1 into, I'm using the vertex form because it's easier, I think, to plug into. So 1 minus 4, negative 3, negative 3 squared, 9. There's a negative in front of it, so negative 9 plus 5 is negative 4. 1, negative 4 is my next point. Use the symmetry, so that goes over for 7 as well. Okay. So that's enough to get a good shape for my quadratic. Okay. Yes, I know you have a calculator right in front of it. You want to check me? Plug it in. Okay. And there's nothing stopping you on the final exam. Okay. Use your calculator. I'm just trying to show you everything that really you should be able to do without your calculator in an ideal world. So there it is. Check the table. If you don't believe my values, there they are. Okay? Yes, sir.
So whenever we went over 4 units, and then we
Yes.
reflected,
Yes.
You're doing reflecting first before you go up 5 units.
Yes.
Yes. Order of operation.
Yes. Yes. Good question. Okay. So the reflection does happen before we go up 5 units because, like we said, it's the order of operations. Okay. We start here. We subtract 4, so that moves us right. The squared, okay, that's just a function. Then we multiply before we add. Okay, so it's going to flip it over and then shift up the whole thing. Good question. All right. Domain. What's the domain of a quadratic? All real numbers. How about our range?
Y is less than 5.
Yep. Y is less than or equal to 5 because 5 is the Y value of our vertex. How many roots? 2. What are our other possibilities? 0 and 1. Okay. We can touch the x-axis with a quadratic in one place, or we can never cross it. And we can end up, what kind of roots do we end up with in that situation? Imaginary. Imaginary. Okay, if it does not cross the x-axis, then we have imaginary roots. Okay, we have imaginary or complex. Both those words kind of mean the same thing. All right, in behavior, what are the ends of our function doing here? They're both going to negative infinity. Okay, both ends are pointed down, so our y values are headed towards negative infinity. Okay, so are we increasing or decreasing first? Increasing, okay, always moving left to right. So we start at negative infinity until we get to 4. We are increasing. And then from 4 to positive infinity, we are decreasing. This is what usually throws people for a loop here. Our y values are going to negative infinity, but our decreasing interval has a positive infinity. Okay? It's because we're going left to right with x values. So negative infinity is the far left, positive infinity is the far right. Yes, our y values are going to negative infinity, but we use the x values. Okay, always using the x values on these intervals. There was something else I was going to say about that, and I lost it. Oh well, maybe it'll come to me later. All right, let's look at this last one, number 4 here. Okay, another absolute value function. We're not shifting it left or right, but we do reflect across the x-axis because of that negative in front, and then we go up 6 units. Okay, again, order of operations, that multiplying by the negative comes first, so we flip it over, and then we shift the entire thing up 6 units. So our vertex is going to be at the point 0, 6. See how straight I can keep my line. Woo, pretty close. All right, that's what our absolute value function is going to look like here. Again, the parent function is, of course, just y equals the absolute value of x. You're talking about the very basic function, okay? You don't want anything added, subtracted, multiplied, or anything. All right, domain, all real numbers. Never changes, okay? Never changes. The only functions that we have talked about so far that are not all real numbers for the domain are logarithmic functions. Those are the only ones that don't have a domain of all real numbers. But bless you, all the other ones we've done, all real numbers. Okay, how about this range? Y is less than or equal to 6, because we have a maximum value there at 6. Still have 2 roots for this one, but it's not a guarantee. Could have 1 or none. In behavior, both these ends going down to negative infinity. This one's similar to the previous one. We start by increasing, so negative infinity until we get to what number? 0, okay? And then 0 to positive infinity. Okay, so I think